Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and in this video we're going to be continuing our discussion of calculus-based physics by introducing the integral, and specifically definite integrals. A quick caveat before we dive in. In this video, we're only going to be scratching the surface of definite integrals, and you're going to be going a lot more in depth in them in your calc class. But we've got a limited amount of time, and we really want to help you guys in your physics classes, so we're going to be focusing on how you can use these tools to do what you need to in your physics class, as opposed to some of the whys on how they work. Your calculus class is going to cover that. So, let's begin. We have an integral, but what the heck is an integral? Well, that's a very good question. An integral is the area underneath a curve, underneath a function or a line on a graph. So like say I have this parabola here, the integral of my parabola over this range would be the area underneath my parabola. Just like how a derivative is the slope of a line, the integral is the area underneath a line on a graph. But I can't exactly calculate the area of this by drawing a circle or something. That's kind of a weird shape. So instead I'm going to kind of cheat. I'm going to draw some rectangles because those I know how to find the area of. I've had that one down for a while. The area of a rectangle is just base times height, and so I could cut my function up into a bunch of little rectangles and calculate the area of those rectangles. And I wouldn't be exactly right, but I'd be kind of right, which is good enough for me. So how would I calculate the area of each of my little rectangles here? Well, I could represent it as a sum. So I'm going to add up the area of all of my little rectangles, the height of my rectangles, because the area of a rectangle is base times height. Their height would just be the value of my function at whatever x point I'm at, so just f of x. The width of my rectangles is how far I'm jumping forward on my x-axis every time I draw a rectangle, so that would just be delta x. My first rectangle starts at x naught, so x equals x naught, and my last rectangle ends at x final. So I could represent calculating and adding up the area of all of my rectangles here with this little sum. But it's just base times height, do a bunch of times and adding that together. Problem with my blue rectangles here is I'm not doing a great job of approximating the area with my 4 rectangles here. On my first rectangles here, I'm way overshooting the area and I'm getting a bunch of extra stuff that's not under my graph. And over here in my later rectangles, I'm way undershooting and I'm missing a bunch of my area. So this would be an approximation, but it's not that great of an approximation. But I can make it better by doing more rectangles and making them smaller. So if I just shrunk my delta x and I made my rectangles tinier and I did more of them, well then every time I drew a rectangle and calculated its area, I would overshoot or undershoot way less. I miss less of my area on the right side here and overcount my area less on the left side. And so we could kind of continue this thought process and say, well, I just have to keep making my rectangles skinnier and skinnier and skinnier and doing more and more and more rectangles, and then I would get a perfect calculation of my area. Just like how whenever we were doing derivatives, we said, well, we want to find the slope of our line at a point. So we're going to find the slope between 2 points that are close together and then bring those points closer and closer and closer until they were infinitesimally far apart. Well, we can kind of do the same reasoning here, and that's what integrals are. Integrals mean we're finding the area underneath our line on a graph by drawing infinitely many, infinitesimally thin rectangles, calculating their areas and adding them all up. The way that we notate that is actually very similar to this expression here. So the way that we write integrals, first of all, instead of having our little sigma here for sum, we have another guy for our sum because we're summing up infinitely many things instead of a definite number here. So we use a little swoopy s like this. It's like an s that you really stretched out long, and he stands for sum, just like how sigma stands for sum. And then instead of using a delta x, because each of our rectangles are infinitesimally wide instead of having an actual numerical width, we're going to be using dx instead of delta x. And that dx is sort of like a difference in x, how far I'm going over on my x-axis for every rectangle, but that difference is infinitesimally wide. Sometimes you'll hear people call this a differential, but just dx, difference in x, how wide each of my rectangles are. So I could represent this same idea as an integral by swapping out my sigma for a little swoopy s guy. The height of my function is still the same. The height of my rectangles is unchanged, but their width is now dx instead of delta x. My starting and end points are unchanged. So here I have x naught, and here I have x final. And that is how I could represent this same guy as an integral instead of a sum. All right, so that's the notation. Let's talk about how we actually use it. But before I go into that, I'd like to take us on a trip down memory lane back to those halcyon days in your elementary school when math didn't have infinitesimals and indefinites and infinities and all of these gross imaginary numbers. Let's think back to when you were learning multiplication and division. Well, first you learned multiplication, and then your teachers taught you division, probably with some explanation that was kind of along the lines of it's the opposite of multiplication. Like if 2 times 3 is 6, then 6 divided by 3 is 2. So the secret that I haven't told you about integrals yet is that they have that exact same relationship to derivatives as division does to multiplication. If velocity is the derivative of position, then position is the antiderivative of velocity. For that reason, integrals are often also called antiderivatives. So derivatives. Spelling is not my strong suit, guys. Okay, so if velocity is the derivative of position, position is the antiderivative or integral of velocity. If 3 times 2 is 6, then 6 divided by 3 is 2. It's the same kind of relationship. So to calculate a lot of integrals, we're going to just be doing derivatives backwards because they're literally backwards derivatives, antiderivatives. So let's think a little bit about how derivatives work. I'm going to erase some of these notes over here so I have room. Let's talk back about one of the first rules you learned whenever you were learning to calculate derivatives, the power rule. The power rule just tells us if I have a function that is x raised to some exponent n, and then I take the derivative of that, then the derivative of my function is going to be equal to n times my function to the n minus 1 power. I subtract 1 from my exponent, pull him down to the front, and multiply him at the front of my guy. And that's how we find the derivative of a function where I have an exponent. So if we think about this backwards, if I start with f of x is equal to n times x to the n minus 1, and I'm trying to rewind the clock to figure out what my original function would have been. Well, I know whenever I take the derivative of an exponent, I subtract 1. So to get back to my original function, I should add 1. So I have n minus 1 plus 1. Okay, and I also know that whenever I take a derivative of an exponent, I multiply my exponent to the front as a coefficient. So I would take this exponent and multiply it down to the front, so I should divide by it. So I had my coefficient here, coefficients stay, but I also have to remember to divide by that n minus 1 plus 1, because I would multiply him whenever I take the derivative. So if this is the result of multiplying, then to undo that I have to divide. So, well, n minus 1 plus 1, that's just n. N minus 1 plus 1 is just n, so I have n divided by n times x to the n, which just simplifies down to x to the nth power. So we have to try and learn how to think backwards and rewind the clock back from whenever we took a derivative. That's kind of a hard idea, and we will be doing a lot of practice with it. So let's run through a couple of quick practice problems, and we'll go through more applications of this in future videos. Don't worry, we're going to be spending a lot of time learning how to use these. So, a good first example, I'm going to leave this guy up here for our reference. A good first example is, let's think if we had like a really nice, pretty line. Like one of the simplest functions we know. I say here I have x, here I have f of x, and then my graph is just a lovely, nice line where f of x is equal to x. Okay, and I want to find the area underneath this graph, starting at 0 and going all the way to here. So say x equals 4. And I want to find this area here, this area under my curve. By the way, as a quick side note, a definition for you guys. In this video, we're talking about definite integrals, which means we have a distinct starting point and ending point that we're calculating the area underneath our curve between. In later videos, we will go into indefinite integrals, which is just where you're finding a general expression for the area under your curve at any point. But for now, we're sticking with the concrete numbers before we take those numbers away and deal with the abstract, because there are a few complicating steps that we'll get into. But for now, I want to find the area underneath my curve here, starting at 0 and ending at 4. So if f of x is equal to x, I'm trying to find the integral of this, starting at 0, going to 4, of f of x. That's the height of each of my infinitely many rectangles, and each of my rectangles are infinitesimally wide, so I put my dx here. You can say this out loud as the integral of f of x with respect to x. That's often something you'll hear people say, just like how you take a derivative with respect to x, and that's just telling you which variable is on your x-axis. People often will read integrals aloud in the same way. So I could either say f of x dx or the integral of f of x with respect to x evaluated from 0 to 4. And that is how I would say that. Okay, so I need the integral evaluated from 0 to 4. Well, my f of x is just x dx. So now we need to think of which function, when I take the derivative of it, would give me just x. So x to the first specifically. Well, whenever I take the derivative of a function, I subtract 1 from my exponent. So I should add 1 back to my exponent to undo it. So that would give me, I'm going to move over here. Well, 1 plus 1 is 2. So x squared, x to the power of 1 plus 1. Because I know whenever I take the derivative, I would subtract 1. So if I need to rewind that clock, I need to add 1 to what I had. But then also whenever I take the derivative, I take my exponent and I multiply him down to the front. So to undo that, I need to divide by what that value would have been, which is my new exponent, which would have been 1 over 2. So I'm going to erase that 1 plus 1 and just leave 2. So the antiderivative of x to the first is 1/2 x squared. And we can check that by very quickly applying the power rule to 1/2 x squared. So whenever I take the derivative of 1/2 x squared, I subtract 1 from my 2. 2 minus 1 is 1, and then I multiply my 2 down in front. 1/2 times 2 is 1, and I'm left back with just a plain old x, which is what I want. So the antiderivative of x to the first is 1/2 x squared, and we're evaluating this from x equals 0 to 4. So this long straight line that I'm using is just for me to remember where my starting and end points are, where I need to evaluate this function as my finish line and my starting line, this 4 and this 0. So I don't use the little s anymore because I've already applied the antiderivative part, but I need to remember to apply my starting and ending points. So we use the straight line at the end to help us do that. And the way I do that is by evaluating this expression here at x equals 4, and then subtracting where I started at x equals 0. So this means I have 1/2 times 4 squared, and then I'm going to subtract this same expression evaluated at x equals 0. So that would be 1/2 times 0 squared. Well, thankfully, that's just 0. 0 squared is 0, times 1/2 is 0, so that goes away. I can ignore him. 1/2 of 4 squared, well 4 squared is 16, half of 16 is 8, so this is just equal to 8, and that is the area underneath my line from x equals 0 to x equals 4. Now, we can double check that because we're very smart and we've passed geometry by this point. So we know how to calculate the area of a triangle, hopefully. The area of a triangle is 1/2 base times height. The base of my triangle here is just 4. Its height would also be 4. 1/2 of 4 times 4, 1/2 base times height is 1/2 4 times 4. 4 times 4 is 16, divided by 2 is 8. So this is also 8, which uncannily enough is exactly the same as the math we got by taking our integral. So our new fancy math still works just as well as math you did in middle school. Great. Okay, but let's do an example where that middle school math falls apart and wouldn't be able to help us. Let's say instead of a pretty little line that draws a nice triangle, we have something a little grosser. Something like, say, a quadratic. So let's say I had a function that looked something like this. Here's my f of x. Here's my x-axis. And say my function looked a little something like this. And so this is f of x is equal to x squared minus 2x. And I wanted to find the area of this function and this space here, starting at x equals 0 and going to x equals 2 meters. So this area here is not really under our curve. And this is why I put little quotation marks under my definition earlier. When we say under a curve, we don't necessarily mean beneath. We mean the area between our curve and the x-axis. So if our line is below the x-axis, that area under our curve is the area beneath our line in the x-axis. Just a quick little note for you guys there. So let's try to figure out what that area would be. Well, if I want to do that, I just have to take the integral of f of x with respect to x, starting from my starting point here, which is 0, and going to 2. Well, my function, I'm going to plug him in now, goes from 0 to 2, and he is x squared minus 2x dx. So now we just have to think about which function, whenever I take the derivative of it, would give me x squared minus 2x. And so that's how we're going to get back to the antiderivative. So thankfully, whenever we take an antiderivative, we can think about each term in a polynomial separately, just like you could whenever you were taking derivatives earlier. If you had x to the 4th plus 5x squared, you take the derivative of the x to the 4th, then the derivative of the 5x squared. If you have things being added or subtracted in a function, you can take the derivative of each of those guys separately and add them together at the end. We can do the same idea with integrals. We can take the antiderivative of our first guy, then the antiderivative of our minus 2x, and just add those together at the end. So first, which function, whenever I take its derivative, gives me a derivative of x squared? Well, we would be subtracting 1 from our exponent, so I need to add 1 in order to undo that. So 2 plus 1 is 3. So the derivative of x cubed would be like x squared. But also, whenever I took the derivative of this, I would have to multiply my 3 to the front. But I don't have a 3 here, so I had to have had a fraction of 1/3 in order to cancel that out. So if I go back and I take the derivative of this, 3 minus 1 is 2. Then I multiply my 3 down at the front. So I keep my coefficient of 1/3, and this gets me back to x squared. So just as a quick little check. So this would be the antiderivative of x squared. Then I have minus 2x. So we have to think which function, when I take the derivative of it, would give me minus 2x. I'm going to leave my minus 2 at the front because he's my coefficient. He doesn't go away. Quick reminder that this is x to the first, so we're still applying that power rule but backwards. I would add 1 to 1 to get x squared, but then whenever I did this, I would multiply my 2 down in front, so I have to make sure to divide that in order to undo that multiplication that will happen. So if I took the derivative of this, I have minus 2 divided by 2, which simplifies down to 1. Minus 1x squared. If I took the derivative of this, 2 would come down in front and would decrease to an exponent of 1, so this would become minus 2x, which is what I wanted. And then we're evaluating this from 0 to 2, so we're just going to plug in 0 and 2 for x. So I have 1/3 times 2 cubed minus 2 squared, and then I'm going to evaluate this at x equals 0 and subtract it, so minus 1/3 times 0 cubed minus 0 squared. Thankfully 0 squared is 0, 0 cubed is 0, this whole thing is 0, so I can just ignore him. 2 cubed is 8, 1/3 of 8 is 8/3, 2 squared is 4, 4 is equal to 12/3. 8/3 minus 12/3 is equal to negative 4/3. So that would be the area of this. But wait, we're not used to seeing negative areas generally. That's not something we ever really deal with. It's like you can't walk negative 2 feet. You can't have a negative area. But here, this negative is just letting us know which direction our area is facing. So because we are below the x-axis, we have an area that is negative because the area is underneath our x-axis. So that would just be equal to negative 1.33 meters. That's a really gross. All right, thank you so much for sticking with me through all that. I know this is a lot. Integrals can be kind of overwhelming at first, but I promise you we're going to do more and more practice with them, and by the time you get to the end of this semester, you will be a master of them. If these videos are helping you, please let us know with a like, comment, maybe even a subscribe so that you can get notifications whenever we release new videos, because we are constantly making new videos. Thank you so much for sticking with me through all that, and y'all, happy physicsing!